crossing, and the strength of that avoided crossing is 2g over 2 pi, where the 2's cancel, so just g over pi. Okay, so they couple to each other, but now the very interesting point is that they couple to each other, as shown here, but there still is this decoherence-free frequency where neither of the qubits is actually talking to their 50 ohms. And so we've achieved the goal of having two qubits talk to each other, but they don't talk to the 50 ohm environment. And that's what we wanted to do. This is a protected decoherence-free subspace. Now, there are many things we can do to couple or to engineer the coupling spectra. One is the number of coupling points. So we just saw that we coupled the qubit at 2 points, and it has 1 minima in the decay rate. Turns out, if we couple it at 3 points, we now have 2 minima. And if we couple it at 4 points, we now have 3 minima, so n minus 1 minima. We can also, if we have more than 2 coupling points, we can change the relative size of them. So gamma 2 over gamma 1. You can see here, this is just one example of 0.5. But as we change that ratio, you can see how the coupling spectra changes. Okay, and then of course we already talked that the distance between the coupling points also matters. So with this, we're able to design coupling spectra. So to do a demonstration, we decided on the following. So we have, again, 2 qubits, but we're now coupling them at 3 points each. The size of the coupling of the dot indicates the strength of the coupling, and the spacing is not necessarily all equal. This is a picture, and if you follow this waveguide back and forth, you'll see that it in fact couples to each qubit 3 times rather than 2 in the way that we've described, and we've made the length of these corresponding to the phases we wanted to achieve. And those phases are shown here just for the numbers. Phi 1 is about phi 3 and half of phi 2, and the coupling strength gamma 2 is about 4 times gamma 1. So that was a design choice that we made. So when we look at this, what we find is that the coupling strength, which is shown in red when the 2 qubits are on resonance, features are shown here. Okay, so it has this coupling strength. And the decay rate, shown in blue, has 2 minima now, as we'd expect, and we can park the qubits at their own frequency, right? Meaning that they're not exchanging with each other because they're off resonance. But if we put them both at the same frequency, then they do talk to each other. And whether we're in this minima or this minima, they both couple with the same strength. So this is an interesting design. Okay, so the test is to create an entangled state. And we start with 2 qubits. We park qubit A and qubit B in their own decoherence-free subspace, different frequencies, so they don't talk to each other. They start out in their ground state, but we'll do a pi pulse to qubit B, which puts B in the excited state. We'll then move qubit A in frequency on resonance with qubit B. They're both here, and they interact with each other for some time tau. And then we move it back, and then we do readout. This creates what's called an exchange interaction, or I-swap type gate, and you can see that the excitations shown in the dark color will oscillate back and forth between these two as a function of time. And maybe this is clearer here, where you can see the population of qubit A and B, they exchange that energy with one another. Now, if we take this point right here, we can effectively stop it halfway, so only half a photon in some language is swapped, and that creates this entangled state 0, 1 minus I 1, 0, which is called an I-swap gate, or square root of swap. And if we look at the fidelity of this gate in the usual way, the fidelity is about 94%. Now, that's not a world record by any means for superconducting qubits. We can do this with more than 3/9 fidelity under very controlled situation. But remember, these 2 qubits are very strongly coupled to an open environment. They would decay at a rate of 10 or 20 nanoseconds, very, very fast. And yet we can create this state. This process would take 100 nanoseconds or even longer. Okay, so we can entangle 2 qubits despite the strong coupling to the open environment using a giant atom approach. Now, the second part that I'd like to talk about is directional, or sometimes this is called chiral photon emission. And what I'd like to motivate here is the reason we want to do this is for quantum networks. And so Quantum networks are important because we need to communicate between different parts of a chip. Maybe the qubits aren't next to each other. And the idea is that you'd have two qubits that are non-local. You want them to talk to each other by exchanging a photon. This is currently done in a couple ways. You couple via cavity, which has high fidelity but has certain limitations. Or you can do it much like we're going to do it now, but in this previous approaches they've had to use isolators or circulators, which are lossy. So this makes it unidirectional. So anyways, the current approach is not great. And what we're going to do is use now what's called a giant molecule, or an entangled state of two qubits that are spatially separated. So the setup is as follows. You have two qubits, qubit 1 and qubit 2, each with a resonance frequency omega, and we can put them into this entangled state. I'll now use the notation E for excited state, G for ground state. So EG plus a phase, GE. Now that phase is going to become important. Here it is plus pi over 2, remember that. And these two qubits are coupled to a waveguide, an open waveguide, that's separated by lambda over 4. Okay, so this is a giant molecule. Each atom is coupled at one point, but once they're entangled, it's one unit, or a molecule, and they're coupled at 2 points. So this entangled state has one photon. We don't know which qubit it's in, and it will emit a photon, one photon, to the waveguide. Okay, and how do we figure out which way it goes? Well, there are four possibilities. One is that qubit 1 was excited and it emitted its photon, and the photon went to the right. And we can calculate the phases that would go with that. One is the qubit state phase. Well, that's an overall phase, so that's 0, e to the I 0. And the other is the position phase. Well, I'm going to define this as x equals 0, so that's also 0. On the other hand, the rightward photon might have come from qubit 2. And in that case, it has a phase plus pi over 2, which is this one. And then by convention, even though this is plus x lambda over 4, it comes in as a minus sign by convention of a pi over 2. You could do the same for the photons which instead go to the left, but what you find is that there is a sign difference such that this now perfectly destructively interferes with itself. Okay, so we're only left with a rightward going photon. Now, there's one piece that you might have picked up on, which is important, which is that we just showed that qubits can couple to each other via the waveguide. And in fact, that would be a problem here because it alters this simple story I just told. So we actually have to create a coupling also between qubits 1 and 2 that's exactly equal and opposite to the coupling that would occur through the waveguide. And when we do this, this now has this simple, quantum optics interpretation. Now we can do the same, but with a minus pi over 2 and go through the same description of these four paths, but now the rightward photons destructively interfere and only the leftward photon survives. So just by choosing plus or minus pi over 2, we can decide deterministically which way that photon's going to go. Okay. So when we implemented this, we did it with an emitter module, and this is the part that Yasu's group came up with at Tokyo. And the idea is the following, is that this molecule is coupled very strongly to the waveguide, and so we don't want to create the entangled state here. We want it to emit quickly. So we actually, we create the entangled state at 2 qubits 3 and 4. We do that by coupling them together. And then when we're ready to emit, we turn on couplers, which are shown here, which transfer this entangled state down to the emitter qubits, qubit 1 and 2, and then they emit as I described. This is what it looks like. You have qubits 3 and 4 with a coupler between them. Qubits 1 and 2 emit the photon with their coupler to null out the interaction via the waveguide, and then 2 couplers on the sides to shift or shuttle the entangled state down to the emitters. So if we want to generate a photon, we first so imagine all the qubits are in their ground state. We first put qubit 3 in its excited state. We then drive a parametric interaction which basically implements a square root of swap gate, and qubits 3 and 4 are now entangled. When we're ready to emit, we drive these 2 couplers which bring the entangled state from the top down to the bottom, and then they emit quickly. And we have photodetectors outside. I'll be glad to answer questions. I won't go into exactly how we do that. But we can detect at room temperature whether the photon went to the right or to the left. Let me grab it.